minus part. No, I'm sorry, plus the hyperbolic tangent of gamma L. Now, I gotta tell you this. You use this equation only if transmission line is lossy. So only if it's lossy. The one we use 99.999% of the times is assuming the transmission line isn't lossy. Because why would you use a lossy transmission line? All right? Sometimes you're stuck with it, and you gotta work around it. But almost always, you can assume that the transmission line, for any real problem, is about losses. So this is the equation we use all the time. And we say Z input, and this is for a lossless T line. By lossless, it means that R prime equals G prime equals 0, or that alpha is approximately 0. That's lossless by definition. Here, it'll have the same form, only it gets rid of the hyperbolics. It just becomes Z naught times ZL plus, and then you're going to have J Whitworth's book. I'm just thinking about something. He doesn't. This plus J Z naught tangent. Now it's just beta times L, because alpha is 0 over Z naught plus J times ZL times tangent of beta L. And I've got to tell you one thing about this. If you let gamma here just be real, strict imaginary, gamma was just J beta, it would turn into that equation. This is the one we use all the time. And it's for a lossless line. It's the input impedance. Are you good with that, everyone? Okay. I try to work more examples, but I have to get this theory out. So that's the input impedance to this line. There is an assumption. Does anybody remember the assumption about the length of the line and wavelength? Anybody at all? How long does it have to be before it actually looks like a transmission line and waves are developed? It has to be 1/10 of a wavelength or longer, right? Just remember that, at least of 1/10 of a wavelength, or else it's just a couple of wires connecting this. So now what we do is this. We look at something called the complete circuit with these equations. Let me redraw something here for you. So here's our circuit. We're going to have a plus to minus Vs here. We're going to have some source resistance. This could be an impedance. Then we're going to have the transmission line. And this transmission line has got a length L. It's got a characteristic impedance Z naught. And it's got a load. ZL, Z load. And there's going to be a voltage at the load and such. Do you all understand this, class? I've just redrawn what I had before. And here's our goal. We want to find out what this is. Matter of fact, what we want to do is try to go ahead and characterize this transmission line's electromagnetic behavior. So work with me here. When I look at this, what I really want to do is find a voltage just on the inside of that transmission line. So label that V prime. All right. And I'm going to assume I have a source voltage Vs. Now, I'm assuming it's in a phasor form, so I could put Vs at an angle of 0 degrees, but it doesn't mean no good. Y'all follow me? I'm just going to leave it as Vs. Why write the 0 if you don't have it? It's a magnitude. So that's just got a magnitude of Vs, but I want to find out how much voltage is developed right there. And the way I do it is, I replace all that by the input impedance I just stated, that's Zn. Y'all follow me? So I'm going to go ahead and redraw this circuit. But now I put in Zn. And my goal is to find out what the voltage is here that I'm labeling as V prime. So how do you do that? Now, you're electrical engineers, you've had circuits. If this is a job interview, they'd expect you to be able to do this in a blink. How do you do that? What is that?
Voltage division.
Simple voltage division, isn't it, class? The only thing I do is take this voltage and multiply it by Zn and divide it by Zn plus Rs. How many know that? Right? Some people say I get the current first. Well, you could, but then when you multiply it by Zn, you're doing what I do. So you can say that V0 prime is really Vs, and it's times Zn over Zn plus, actually Rs, the source resistance. Now I didn't put Zn of L because I'm assuming the input can only be at L right here. Everybody all right with that? Okay. Now, I've got that. What is this equal to? Think back for the equation, I've erased it, of voltage on the line. There's a propagating wave going in the positive direction and a reflected wave in the negative, right? So right here, what this is equal to, that's equal to V0 plus, and it's equal to E. I'm going to do this also for the lossless case only. Give me a full to do this. Well, there's no reason to do it for a lossy case. It's just, yeah, you can, but it's a waste of time because if it's lossy, you're going to redesign it. So here it would be E, and normally it's minus J beta times Z, but Z is minus L. Y'all follow me? Because I position my load here at Z equals 0. That's positive Z, so this is at Z equals minus L. So this becomes J beta L plus the reflection coefficient, whatever that is, e to the minus J beta L. Now here's why we need that. Y'all with me? Add this, bound Zn, from Zn I get V prime, right? V prime is equal to this. What I'm after is my V0 plus. Y'all follow me in that class? And I'm going to do that over here and erase this. All right. So if I look at this, I can say V0 plus is equal to V prime, I'm going to leave it as V prime, over E to the J beta L plus the reflection coefficient times E to the minus J beta L. And that's V0 plus. You all agree with that? And here, I'm just restating what the previous step was. So now that I have that, why would I want that? Remember, the goal was to find the voltage at the load. Well, I know that the voltage anywhere is equal to V0 plus times E to the minus J beta Z plus the reflection coefficient, right? Times E to the plus J beta Z. That's what it is anywhere. Do y'all agree? We've got V0 plus, correct, class? That will be a magnitude at an angle. It will not be just strict real. Remember that. So if I have that, and can y'all read this okay in the far back, guys? Okay? If I have that, how do I get the voltage at the load? What is the one thing I do to this equation? If I want the voltage at the load, where is the load? Z equals 0. Y'all follow me? So the voltage at the load at Z equals 0 is V of the load, and that's simply V0 plus e to the J0 is 1 plus gamma L. And that's the voltage at the load. I'm going to ask you a question. Do y'all agree with that? The voltage at the load. How do I get current at the load? Just think. That's it. Just divide by the load impedance. Does that make sense to you? How do I get power at the load? I can put it up here just for completeness. I can say, therefore, I at the load would be equal to V at the load over Z of load, right? How do I get power? Remember, these are phasors. This represents like 10 at an angle of 0 degrees kind of thing. And it's a peak voltage. So how do you get power? Back from your circuits work.
VI conjugate?
Well, yes, but this is not RMS voltage and current. These are peaks. So what is it? P at the load would be, technically this is the, if we're using peak values for voltage as the driver, it would be 1/2 times the real part of V times I conjugated. Now the total power, I don't remember if Irwin did this, but V times I conjugate has the real power in it, but it also has an imaginary or reactive power. Do you all remember reactive or not? Irwin, I don't remember how much you talked about. Did you have gross for power in here or not? Oh, you know it. How many had gross or had the power course? If you had it, you got this down. If you haven't, don't worry about it. Anyway, it's the real part. Now, I've got V, right? I got I. You know how to take a conjugate of that, correct, class? You can do that and get this. Here's the trick. If ZL is resistive, pure real, that power is just V at the load squared divided by 2 divided by the resistance. Right? If it's pure reactive, the real power is 0. A capacitor or an inductor does not absorb, it has no real power consumption. Y'all with me on this? All the power is reflected, so if it's an inductor or a resistor. If it's a combination, it's got a real and imaginary part, or magnitude and angle at not 0, you gotta do this. Okay? All right. So that's the whole circuit. And we can work through a problem. They're a little tedious right here because there's a lot of little steps and you have to get good with your calculators. Here's one piece of advice. Equations like this, and that impedance equation I put in there, Zn is equal to Z0 times ZL plus J Z0 tangent of B. People mess that up all the time. Get used to using your calculators to calculate and get the right answer. I will give you problems. You can confirm you know what you're doing. Do not assume you know what you're doing because you're going to lose points. And I kind of hit hard on that because some of the answers are insane. Like a Zn of an infinite amount, and then you got a load voltage. Well, if you got an infinite input of P's, there's no current flowing in. I'm not going to get into this right now, but you have to, as engineers, come up with some, at least, appreciation for reality when you do your math. Insanity is not needed here. We've got enough of it elsewhere. You'll see it in the real world, trust me, with designs. You'll see bridges collapse because the guy just, well, your computer program said that. If you don't know what I'm talking about, you haven't really lived long enough to appreciate how bad some of the blunders are. All right. That's average power. Now what I'm going to do is what I really came to do today is a Smith chart business. Now, people at first glance look at Smith charts and like, huh? So I'm going to show you, I haven't done it in a while. I mean, I could go through the development of how the Smith chart came about. Realize this, that whole thing is based on the reflection coefficient and getting curves of constant reflection coefficient. It's in the book. I'll give you links so you can read it yourself. It takes a while to do it. Years ago, we used to do it all the time, but wasted an entire class period. And most of the kids, most of the students, if they're really interested, they'll do it themselves. But practically speaking, what you want to know is how to use it. You know that it's simply a chart that is a graphical representation of equations for reflection based on normalization. You'll get that in a second. So, here's the Smith chart. Start a new piece of paper. Now, if you have one, you can just pull it out and reference it. You reference everything I'm saying. And I sent you a pretty good one, didn't I? There's one in the book. I see these guys book open to it. Normally what I tell people to do, I would print out about 10 of them. 10 with the resolution you feel you need. Because they're all over the place. You can find very, very detailed Smith charts, and you can find horrible Smith charts. Try to find one. The one I gave you is pretty good. I think it's pretty clear. So a Smith chart starts off looking like a giant circle, like so. And then after that, the next thing I always do is say, put in the equator. So just right across here, draw a line. Then find the center of this. Then put in another circle that snugly fits between these 2 points. As such. You got that? Now, what I'm going to tell you is, with Smith charts, we start when we take a Smith chart and we create something called a normalized load impedance, ZL. And we take the actual load impedance, ZL, and divide it by the characteristic impedance of a transmission line. So everything I'm talking about is related to transmission line theory. Y'all with me? Now, this will have some real plus some imaginary component. Y'all with me? Everybody? You can look on your Smith chart in a second. So how do we go about finding that in this crazy thing? Well, this circle I drew here, that goes right through the center, is called the R equals 1 circle. It represents the entire range that R equal 1 normalization for that ZL could have. Y'all following? Then there's something that runs perpendicular to this. And these are lines that intersect normal to the entire rim of the circle. This would be J1. That's the imaginary part. You'll see down here at the South Pole, there'll be minus J1. And let me continue with my thought. Now, what you really have with the Smith chart is you have circles that are, they're centered on this horizontal axis, same one, but they're just real values. For instance, R equals 2 is about here. R equals 0.3 is here. And R equals 0 is this big outer rim. You with me? I know it's a lot to take in, but when you do this, the way I'm showing you it, I think you'll appreciate why I'm showing you this way. Now, you see these imaginary things? I've got J equals plus 1, minus 1. There can't be a negative resistance. That's why it doesn't exist on this plot. You follow me, guys? But there can be a negative reactance. It can be minus J something. So here, what you're going to see is you're going to have trajectories. This would be minus J, like 2. This would be plus J2, plus J3, plus J4, or 3 here, pardon me, plus J3, and so forth. And as it comes out here, it would be like plus J 0.2 or minus J 0.2, smaller and smaller values. Now on your Smith chart, you'll see these families of curves, these trajectories, if you will. And here's something important to know. When you're looking at this, I told you this is the first point, right? After you normalize your load, you get a real and imaginary component. So if the real component, let's just give you an example. If this was 1 plus J1, if it was that, then you take your Smith chart, see if you can identify this, and you find this R=1 circle. It's the one that goes right through the center, and you'll see 1 on it. Trace along that line until you hit J1. And this point would represent 1 plus J1 on the Smith chart. Y'all follow me? So why are we doing that? That's a good question. Well, this is where it gets interesting. For starters, what this represents is something of magnitude of the reflection coefficient. And the angle of the reflection coefficient, if you look at your Smith chart, you're going to see out here an angular measurement in degrees. And this will be angle of reflection coefficient. For a second, take a look at the outer part of the rim. You all see something in degrees, or it should be in degrees, not radians. You all see it? You got your Smith charts, guys? How many have a Smith chart accessible right now? If you don't, make sure you look this up and see it, because you're going to need to, all right, in degrees. So I said that's gamma L. Well, it doesn't have a length on here. So how do you know it? Because if you take this distance and you go down at the very bottom of your Smith chart, let me see if I can do it here in my book. What page is that Smith chart on?
63. 63?
63?
Yeah.
Go at the very bottom here in the Smith chart, you're going to see something where it says reflection coefficient E or I. Do you see that, the very bottom one? E represents voltage. It's the old English way of representing voltage, or current reflection coefficient. And if you take the length of this, and you need, this is why you need a compass, or you actually need some way of gauging the length of this. The compass is perfect because you have different radiuses. You go here and you put it at the bottom there, and you can see when you measure that, the smaller the reflection coefficient, the closer to 0. You always start measuring at this end, and the greatest possible value of reflection coefficient would be 1. You'll see you can measure it right there. You all see that? There's a lot more that we're going to do with the Smith chart, but I want you to appreciate that part. Next then. So, this is the real, that's interesting, but it's nothing as important as I'm about to show you. So when you come in on a Smith chart here, this would be your first point. And I always tell people to label. That's where I entered the Smith chart, right? Now, what you normally do is take your compass and make a circle. Plant the point of the compass right in the center here and make a circle of constant radius. Y'all with me? So that's the radius at the center, and I'm just showing you a circle of that radius. Can y'all follow me, class? I'm going to send you some videos that are excellent on this after this class. Now, take your straight edge and go from the center right through this point and whip it out here through just a straight line from the center of the circle through the point where you entered, and it comes out here. And then you're going to see two things if you look carefully on your Smith chart. And they're near this side of it. And it will say wavelengths towards generator. And then you'll see something wavelengths towards load. WTG and WTL. You're going to see them on the outer rim. Can you all see that? Please take a moment. I want to finish this thought here. You guys got Smith charts back there? Can you see this? All right. Wavelengths towards generator is the only way you can move from a load. The generator is at the other end. You all follow me? So now the next thing is you're out here and you're going to see a number in the wavelengths towards generator demarcation zone, it'll have something, I don't know what it is, but it'll have a value out here. Think of that as a highway mile marker. Got me on that? Think of it. If I wanted to go 5 miles and I was at mile marker 57, I would need to get to mile marker 52 if there is one. You with me on that? We use this as a reference. So we come in, you're gonna have a certain something wavelength. Now, if you're moving wavelength to generator, that's the only way you can move if you're at the load, then you're gonna be moving in this direction. Well, in his thing, he'll show you an arrow, I think. You know, I'm sorry. And here, I got this is wrong. This is wavelengths towards generator. You're moving this way. Take a look and you'll see an arrow that shows how you move in that direction. Can you all see that? Guys? You have a book there or not? Do you have your book or not? Yeah. I mean, I'm just trying to make absolutely certain I'm clear about this. So you move in the direction of wavelengths to generator. How far do you go is the next logical question. That's what you want to do. What am I really after here? I'm after the input impedance for starters. So for this thing, it has a certain number of blank, call it alpha, wavelengths long. Y'all follow me? I move that many wavelengths if I want to know the input impedance. Now just listen to this last segment, I'm going to let you go. So I come in here, then I move, I figure out how far I'd be. Say if this was 0.1 and I've got a 0.5 long, make it 0.2 long wave, or 0.2 wavelengths long line. So I would find the marker where it was 0.3 wavelength. Y'all with me, class? I'm just adding it. So somewhere down here would be where the line length was added to this entry point. So this would be, I'll call it the at generator. This is where the generator would be. And now the only thing I do when I find this is I take my straight edge, draw through there, and then I'm going to have a point where I have a new value of Rn Jx. Do y'all hear me? This one was 1 plus J1. Y'all with me? Now I moved, and I'm still going to move, technically the way they show it a lot of times is this. You're moving along this trajectory until you move the length of the line. Down here I'm going to have something else. I'm going to have a real and imaginary part that are going to be quite different than my original. Then to get the actual value of the input impedance, you multiply it by Z0. Now, I'm over by a couple of minutes, so I owe you some time, but thank you for staying with me. I'm going to send you some information about this on video links. The quiz on Monday will not be on the Smith chart, but I want you to do some work with the Smith chart. Y'all hear me? Come prepared and have plenty of them. And bring your compass and straight edge. Do not get behind in this class at this point, because this stuff will eat you. I mean, you will not have a good quarter, or good semester, I should say, if you get behind. All right.